No matter how much we study space, our brains are simply not capable of truly grasping the astonishing fact that the universe is infinite. However, a recent discovery may give scientists a reason to rethink everything. Is it possible that the universe has a boundary? And what is the blazing wall that National Aeronautics and Space Administration probes discovered at the edge of the solar system? Scientific researchers have been discussing the existence of an intergalactic boundary between the solar system and interstellar space for a long time. However, until recently, humanity's technological capabilities did not allow us to obtain data from such distant regions. Everything changed thanks to National Aeronautics and Space Administration space probes. The strange glowing wall at the edge of the solar system was first discovered in 1992 with the help of a spacecraft. At that time, scientists only considered the existence of this barrier in theory. However, from 2007 to 2017, National Aeronautics and Space Administration scientists launched the New Horizons spacecraft and scanned the sky 7 times to determine the presence of a strange ultraviolet light, which was detected by Voyager 1 30 years ago at the so-called edge of the solar system. The spacecraft obtained a 360-degree view of this ultraviolet emission and confirmed the detection of excess ultraviolet light far from the Sun. Its data is almost identical to the measurements that Voyager 1 made. We see the boundary between the neighborhood of the Sun and the galaxy, says Leslie Yang from the Southwest Research Institute. What is this boundary and why did it form? The fact is that all the planets of the solar system are under the influence of the so-called solar wind. This is a continuous stream of charged particles emitted by the solar corona, forming plasma. It is this plasma that creates the heliosphere around our entire system in the shape of an elongated bubble. However, at the boundary of the solar system, the solar wind completely dies down, and beyond it begins interstellar space, which is mostly filled with hydrogen. The glowing wall discovered by Voyager is the result of the collision between the solar wind and interstellar forces from neutral hydrogen atoms. It is assumed that helium particles, when colliding with hydrogen, lose their speed, their kinetic energy is converted into heat, and at the boundary, a so-called hydrogen wall is formed, which scatters ultraviolet light in a special way. Does this mean that the National Aeronautics and Space Administration probe could literally run into a wall? To answer this question, let's take a look at what this boundary actually is. Officially, scientists have called this barrier the Wall of Fire. Let's imagine that we are passengers on the Voyager probe looking out the window. Our location is 90 astronomical units from the Sun. The device is gradually approaching the hydrogen wall. The first thing you see in front of you is the area where the solar wind can no longer withstand the interstellar wind. First, a shock wave forms in the heliosphere, an area where the wind speed drops sharply, but its density increases. Thanks to National Aeronautics and Space Administration's research, we already know that the magnetic field here has a strange structure resembling foam. This happens because magnetized matter and small cosmic objects create local magnetic fields, which can be compared to bubbles. Next, we fly through the heliosheath. Our location is 100 astronomical units from the Sun. This is a zone of turbulence where the solar wind slows down and compresses. When the speed of the solar wind gradually drops to zero, we enter the so-called heliopause. Here, the pressure of the solar wind is no longer able to push back the interstellar matter. As a result, the solar wind mixes with the interstellar medium. And finally, here it is, the boundary made of the hydrogen wall. Even though there are no border guards here, it will be difficult for us to pass through this area without complications. You could say it resembles a real hell. The hydrogen wall contains colossal masses of scorching plasma. According to the data from Space Probe 2, the temperature here ranges from 30 to 50,000 degrees Celsius. Such a hot wall creates a kind of barrier that protects our solar system and prevents about 70% of cosmic radiation from passing through. That's reassuring because if this protection fails under certain circumstances, we would automatically end up in interstellar space. Most likely, we wouldn't be able to survive in such conditions due to the high level of radiation. If that happened, life on Earth would look like scenes from post-apocalyptic or nuclear winter movies. However, the boundary of the solar system has another interesting feature. It has low density, so National Aeronautics and Space Administration probes can pass through it. The main task is to make sure the equipment survives as it flies through the hot plasma. The same can't be said about. Part of its equipment responsible for data transmission broke down when it tried to pass through the scorching barrier. That's why now all our hopes rest on it, which, according to the latest data, hasn't yet reached interstellar space and is temporarily stuck in the transition zone. National Aeronautics and Space Administration scientists continue to receive signals from it, but at the moment they're not sure if it will ever be possible for humans to travel through this barrier of hot plasma. For now, we can't confidently predict how interstellar radiation will affect the passengers of a spacecraft. But let's suppose that our technology has made such a journey possible. What will happen when we fly through plasma? So let's imagine that we've managed to do the impossible. We've crossed the boundary and, in a sense, entered a new reality that has nothing to do with life in the solar system anymore. What happens next? For now, we can only guess about that. There is a hypothesis that behind the wall, a primary shock wave awaits us. It has the shape of a drawn bow and resembles the wave that forms on the surface of water in front of the bow of a moving ship. A primary wave will occur if the interstellar medium is moving toward the sun at supersonic speed. However, this wave may not exist at all. In a study published based on the analysis of data from the probe, it is stated that the speed of our heliosphere moving through the interstellar medium is not high enough for this. The spacecraft data also confirms these conclusions. But in order to determine what exists beyond the hydrogen boundary, we will have to wait for new data. And now it's time to return to the question that was asked at the beginning of the video. Does the universe have a boundary? Since we have established that our solar system has a visible boundary, a logical question arises. Can we apply this pattern to the entire universe? The fact is, in recent years, there have been many scientific discoveries that give us more and more intriguing hints that the universe is not limitless. For example, if we assume that the universe is infinite, then we should talk about its infinity not only in space, but also in time. And that means such a universe would have to have an infinite number of stars. However, when you look at the sky at night, you see dark gaps between the stars. This tells us that the cosmos has not existed forever. And according to the Big Bang Theory, there is a point in time when the universe has a beginning. Our world has not always existed. And all of this disproves the theory of the eternity of the universe, and accordingly, its infinity. The problem is that traveling vast distances takes light years, and therefore scientists always receive outdated data. At the same time, we have only been able to see galaxies as far back as 13 billion years. That is the maximum available to us, claims Neil Cornish, an astrophysicist from Montana State University. Thus, for our vision, there is a barrier of relic radiation that formed 380,000 years after the Big Bang, when the universe expanded and cooled enough for atoms to appear. This radiation can be compared to a baby picture of the cosmos, where it is captured before stars appeared. However, beyond this barrier, there may exist either boundaries or an infinitely continuing universe. We cannot obtain definitive data on whether the universe has a boundary or not, but by using mathematical calculations and studying the microcosm, scientists have already developed working theories, and have even suggested what shape the universe actually has. You can learn more about this from the video I released earlier. Everything in the world has a beginning and an end. That is the fundamental law of existence. If there is a hypothesis about the beginning of our universe in the form of the Big Bang Theory, then what do you think the end of our universe will be like? Will it be a slow and endless dying in eternal emptiness or cold? Or will the end of the universe be marked by a spectacular fireworks display of a completely new kind of supernova? How are these supernovae connected to black dwarfs and iron stars? Where should we start? Maybe from the end? At the moment, the most likely hypothesis for the death of the universe is the so-called heat death. The theory, also known as the Big Freeze, was formulated by Rudolf Clausius in 1865 and was based on the second law of thermodynamics, extrapolated to the entire universe. To put it briefly, when the universe approaches maximum entropy, which is a measure of irreversible energy dissipation, its eternal exponential expansion will lead to absolute emptiness and absolute cold. Stars will gradually cool down and burn out, black holes will evaporate, and the expansion of the universe will become so great that the distance between the remaining particles will be so enormous that they will never cross paths again. Will the end of the universe really be so cold, long, and bleak? In August 2020, a hypothesis appeared suggesting that perhaps the end of existence will be marked by a bright final fireworks display of exploding stars. But to get to that, let's first try to figure out what dying stars will turn into and what the fate of our sun will be. To get to the heart of these mysteries, we'll need to go back to the beginning of the story. Specifically, less than 100 years ago, in the 1930s, while everyone else was enjoying a period of relative peace between the world wars, the scientific world was in the midst of a revolution. The new science of quantum mechanics largely shattered the classical understanding of the world. Ralph Fowler, an English theoretical physicist, for example, discovered a new theoretical state of superdense matter, degenerate matter, in which atoms lose their electrons, and then these electrons are packed so closely together that all possible quantum states are occupied. Fowler's discovery lifted the veil of mystery over the life cycle of stars and their evolution. A new type of star was discovered, white dwarfs. These faint but searingly hot stars have a density so high that 1 cubic centimeter of their material literally weighs a ton. Fowler realized that they could be made of this very degenerate matter, and that the degeneracy pressure alone would be enough to stop their collapse under their own intense gravitational field. This is one of the final stages in the transformation of stars, which first expand into red giants and then contract into white dwarfs. But is this really the fate of all celestial bodies? Fowler's student, Subramanian Chandrasekhar, asked himself this question and realized that it all depends on the star's mass. Chandra, as the scientist was called by his friends, proved that there is an upper mass limit at which a star can evolve into a white dwarf. It was named the Chandrasekhar limit. Stars that are above this limit end their existence in an explosion, which leaves behind a neutron star or a black hole. Stars with less mass, like the Sun, have a completely different evolution, ending up as slowly cooling white dwarfs. But is this the end? Not at all. As stars cool down, the once scorching plasma changes its state. It freezes, and the star begins to crystallize. In ordinary crystals, atoms or molecules are bound into a lattice, sharing their electrons. In a white dwarf, the nuclei will never be able to get their electrons back to become atoms again. The electrons remain as a hot, degenerate plasma and continue their work of preventing the star from collapsing. Meanwhile, the nuclei stop interacting with the electrons and slow down as they cool, becoming almost motionless inside the star. Eventually, all white dwarfs must cool down to the temperature of the surrounding space. Right now, that's a chilly 3 Kelvin, but in the future, They'll become even colder as the universe expands and the cosmic background radiation dissipates. And this is where the final form of a cooled star appears, which is called a black dwarf. It's a completely cooled star that no longer emits any visible radiation. But what if life can still linger, even in it? Could it be that the black dwarf stage is not the end yet? And here we finally come to the very discovery that was made in August 2020 by the theoretical physicist Matt Kaplan. The thing is, black dwarfs have two paths. One of them awaits 99% of all cooled stars, but according to Kaplan, in the icy core of 1% of black dwarfs. There are still processes going on that can turn a dead cooled star into a completely unique type of supernova. What is this about? The first path that most black dwarfs will take is the iron one. But what kind of transformation into iron are we talking about if the star is completely cooled down and all processes inside it have stopped? The thing is, there is a possibility of nuclear fusion that can occur even at very low temperatures, thanks to so-called quantum tunneling. It implies the possibility for particles to move toward each other, even when there isn't enough energy for it. At the same time, these reactions happen so slowly that it can take millions of years before even a single reaction of this kind of synthesis occurs. But what will happen after ages if something like this does happen? So quantum tunneling brings a nucleus close enough to its neighbor for them to fuse into a heavier element. This process is called pycnonuclear fusion, and it very slowly transforms the core of a cooled star from carbon into the most stable form of matter, iron, over the course of about 10 to the power of 1,500 years. As a result, you get an iron star or an iron black dwarf, the hypothetical fate of all stars whose cores are below the Chandrasekhar limit. The fate of the white dwarf hinges on proton stability. If protons decay, the entire star will dissolve into a subatomic mist. In just 10 to the 32nd power years or so, long before it can become an iron star. But if we assume that protons are stable, we will reach a point where the universe consists only of iron stars and radiation. And these iron stars are also doomed. They themselves will quietly become black holes over countless eons, something like 10 to the power of 75 years, and these black holes will evaporate rather quickly compared to them, leaking away as pure radiation over 10 to the power of 60 years. This will happen to 99% of black dwarfs, but what about the remaining 1%? And what kind of supernovae can truly be called black? Here we return to Matt Kaplan and his article. Kaplan found a way for some black dwarfs to end their lives on a brighter note as black dwarf supernovae. Remember that the Chandrasekhar limit gives the maximum mass possible for a stellar remnant to be supported by this pressure. It depends on the number of electrons relative to the mass of the star. Kaplan conducted a detailed analysis of the nuclear reactions that lead to the formation of an iron star and found that their fragile equilibrium is under threat. In the final stage of the pycnonuclear fusion process, 2 silicon nuclei merge to form nickel. Then, one of the protons in the nickel emits a positron, turning into a neutron. As a result, iron 56 is produced, the most stable element in the universe. But this emitted positron is the antimatter counterpart of the electrons that support the star from collapsing. It immediately annihilates with one of these electrons, depleting the star's supply. By the time the iron star is fully formed, its Chandrasekhar mass drops from about 1.4 to less than 1.2 solar masses. This means that a white dwarf, or now an iron black dwarf, which was originally stable with a mass below the original Chandrasekhar limit, can become unstable if its mass is greater than 1.16 solar masses. When this happens, a catastrophic collapse should lead to a new type of supernova, which will occur only in this distant future, the black dwarf supernova. They will leave behind smaller iron cores or neutron stars. For the largest of these stars, the expected time of destruction is about 10 to the power of 1,100 years from now, whereas for those at the lower end, it will take up to 10 to the power of 32,000 years to cease to exist. So apparently at the end of time, we can expect iron stars, as well as black supernovae exploding in an unimaginably distant future of space-time. Let's admit, this prospect looks much more appealing than an endless icy void filled with dead black stars. Unfortunately, or rather fortunately, humanity is unlikely to witness this grand finale of the universe. We're used to taking the moon for granted, but you have to admit, it's still a wonderful sight in our sky. The moon is quite large and close enough to us that we can easily make out surface details with the naked eye, such as the dark lunar seas and craters. Just looking at our satellite through a telescope is already impressive. However, what we're about to show you in this video will outshine even the most powerful telescope. The thing is, humanity has been fortunate not only to visit the moon, but also to launch an orbital spacecraft that circles it and scans the surface with a powerful camera since 2009. So what has it managed to capture? In this video, we will show you some of the latest impressive and mysterious images of the moon taken by National Aeronautics and Space Administration's automated interplanetary station. This is a harmless little unnamed crater. As you can see, there are many tiny craters inside it, and this crater in turn is located inside another crater. If we zoom out, we can see that these craters are not only inside another crater, but their shapes are almost perfect. Both of these craters are designated as one crater, Belli. This peculiar type of crater is known as a donut or concentric crater. It is quite possible that they are the result of two unexpectedly precise meteorite impacts. But here's the question. Could Mother Nature have created something so perfectly even? If the craters were the result of random collisions, then there should be a random distribution of concentric craters on the surface of the moon. However, this is not the case. Take a look at this map. The number of concentric craters increases around certain areas, especially around the edge of this region of the moon called the Ocean of Storms. Another factor to consider is that most of these craters are the same age. Looking for clues inside the crater itself also reveals something interesting. The outer crater should be about twice as deep as other craters of similar size on the surface of the moon. Certainly the reason is the impact from the sky, but there is also some other unknown factor. One theory is that some of these impacts occurred when the surface of the moon in this region was in a state between solid and liquid, with a consistency similar to cold lava or honey. When the impact occurred, it caused a ripple that spread outward, but then stopped and never smoothed out until it was completely cooled and frozen in place. The most likely theory is that when the moon was more geologically active, the craters in this region were pushed up from below by magma, trying to break through to the surface. This explains the shallowness of the crater and why we see concentric craters mostly around certain points on the moon. Although more specialists trust this theory, we still don't know the answer for sure. What do you think it could be? Let's move on to other interesting features. You probably think that the surface of the moon hardly changes at all, except for the occasional meteorite impact. Basically, you're right, but scientists have found evidence that the soil on the moon moves from time to time. In this image, you can see the edge of a large crater, 32 kilometers wide, known as the Kepler crater. And what you can notice along the wall of the crater indicates that landslides have occurred here. Moreover, the dark-colored soil apparently fell down the slope. Let's take a closer look at what's happening by zooming in on the most noticeable landslides in this crater. The material apparently comes from the canyons at the top of the crater. Interestingly, the main mass of this landslide seems to be made up of many smaller ones. So it's likely that all of this didn't happen at once, but over time. The landslides were most likely caused by tiny meteorites hitting the crater wall. These tiny impacts and the resulting landslides round off the edges of the crater. That's why the oldest types of craters on the moon look so smooth compared to the freshest craters. What other mysteries does the moon hold? Here's another one, the remarkable Messier crater. Usually craters are round, but this one is elongated. It looks more like an ellipse with a slit at the very bottom. Things get even more mysterious if you zoom in a little. There are two more craters located right next to Messier crater. The one on the left seems much older than the other, as it appears to be more eroded compared to the fresh impact crater on the right. Did the new crater just cover up the old one? But let's zoom in even further. Actually, the key to understanding these amazing shapes is the lines radiating from the crater. They're called rays, and they show the direction in which space debris traveled after the impact. On round craters, debris can go in all directions, like those that come from the Tycho crater. However, here the debris goes in three different directions, to the north and south from this crater and to the west from it. So what could have caused this? The answer is this. Some object struck the surface at a very low angle, less than 15 degrees. And in this particular case, it turns out that this object broke into three parts before they even hit the surface of the moon. Let's look at another asymmetric crater and try to understand why it has this shape. Although it's quite possible that this crater is also the result of two impacts or a single impactor that broke into two just before colliding with the moon. Scientists believe that in this case, some other forces were involved. Notice the shadows in this image above and below the crater. It's obvious that this crater is right on top of a peak. Zooming in and looking at the topographic map of the region shows that this is exactly the case. Imagine if Everest was suddenly destroyed by a meteorite. The shape of this crater was probably caused not only by the angle at which the impactor approached, but also by the fact that it struck this steep mountain slope. It might not look that steep from an oblique angled shot. However, over a distance of just about 20 kilometers, there is an 8-kilometer difference in elevation from the peak here to the bottom of this neighboring crater. You can't really see much in the next shot. The only thing visible in this vast area is a certain patch of the surface bathed in sunlight. Why is this patch so important to us? This place is located on the edge of the Epinus crater, a crater found near the moon's north pole. Future colonies on the moon will be located somewhat closer to the north and south poles, because here, at the bottom of the craters where the sun never shines, there are large amounts of water ice necessary for the existence of any colony. Water can be used for drinking, washing, cooking, and agriculture. Plus, splitting it into oxygen and hydrogen provides breathable air and rocket fuel. These poles also have an additional advantage. There are peaks here that are almost always in sunlight, unlike other parts of the moon, where the day and night cycle lasts 28 days. The colony's energy system will only benefit from this. However, this is not a perfect solution, since peaks like this one will eventually also be covered in darkness depending on the time of year. But 89% of the time is definitely better than other regions on the moon, where you get sunlight about 50% of the time. Finally, we'll leave you alone with two islands in the darkness found in the Baba crater. These are central peaks located in the middle of this 80-kilometer wide crater. Thank you for watching our video, and be sure to check if you haven't missed other videos on the Hubble channel. Subtitles created by